think I'm online. Cool. Yeah. Hi everyone. Welcome again to the second stream of the day. Another hour of learning with Zach. Yeah. So what are we doing today? So I think if you were here yesterday, I would have tried to write some tests for this CPU that we've been writing over the last few sessions. And it appears I didn't push the code because I didn't feel like it worked good enough so that I would push it in any case. So what we're gonna do today is do some simplification of the code so that it actually runs the way it should, and then we should likely end up doing something like, how do I say this? Try the test again. The thing I realized is the last time, a couple of weeks ago when I was waiting on my mail, I was waiting on this board a couple of weeks ago. I was waiting on this board, which is Pico Ice 2. So I'll show it to you and then I'll show it to you on the screen. I was waiting on this board, which is a Pico Ice 2, and I haven't even unpacked it. I just got it from the mail today. Why does everything have to be complicated on this channel? Even just opening a little nylon paper bag, so hard. Anyways, so for a couple of weeks I've been waiting on this board. I'm gonna show it to you now. I will show it to you now. Finally got it out of the anti-static bar. So this is a Pico Ice 2. And it comes with an Ice 40 FPGA, which is on there, some flash memory, and Raspberry Pi. This is 2350. Pretty cool, if you ask me. And while I was waiting on, the reason I'm showing this board while I'm doing this stream, it's not an unboxing stream. So a couple of weeks ago, while I was waiting for that board, I actually did some explorations and I wrote some. Very basic Verilog, but this Verilog I got it from, I think I fetched it from the Appio samples, and this Verilog has a test bench that actually works. It's actually the one we ran yesterday and works. And as I was going through this, I realized it was much simpler than the one I was trying to implement yesterday by reading, and I realized that the issue with my code, with testing my code yesterday, was because I was using this silicon blue primitives from Lattice. And these primitives basically were holding me back because I couldn't write a test bench or use it. This is a test bench. It's so simple. The one we had yesterday ended up in 3 files. So I think the point of today is to see if we can we build up this same CPU with it's just 3 LEDs and a clock that we're using from the silicon blue primitives. If we can't do that and manage to sort of remove the silicon blue primitives, then it puts us at a very easy place to start using the test benches, because there's no need of going forward and writing more complicated stuff if we don't know how to test it. So the first thing we're going to do now is to try and remove these silicon blue primitives. So this is a silicon blue anything with an SB underscore. Anything that starts with an SB underscore is a silicon blue primitive. And a silicon blue primitive is silicon blue lattice. So, and a silicon blue primitives is this is like years ago. It's years ago. Silicon blue lattice primitives. Oh oh, I see how it works. Someone used to write IPs and lattice both them. And that's why we have Silicon Blue, because Silicon Blue used to be a company. I just learned that on this stream now. That's a way of making money. Write IP, write a lot of IP. Make it work as best as you can. So anyways, this Silicon Blue primitives, they represent this like hardware that really lives on the lattice fabric. Okay, it's already hardware that is on the fabric itself. So that's what it is, and you don't have to write. You can just use it. It's like a pre-made driver, pre-made IP that you can just go and use. So yeah. So anyways, when testing, mocking those out, making the stubs for Silicon Blue primitives is very difficult, and I have not learned how to do that yet. And I am unwilling to stop learning everything I am learning to learn how to stub the Silicon Blue. I would rather go back to bare metal, which is kind of what I really like, because I'm trying to learn this thing all the way up. Yeah, so that's going to be our exercise today, to get rid of this Silicon Blue primitives, and then we'll sort of go from there. And the first thing we need to do in order for us to get rid of the Silicon Blue primitives is we need to sorry, I do have some messages. Is we need to find a way of getting a clock. Luckily for us, we do have this from UPduino. UPduino comes with a way to use an oscillator, or rather, the UPduino board, not the actual lattice itself. The UPduino board has an oscillator, and in order to use this oscillator, we need to select it. So you see, we can route an oscillator into the FPGA directly by just shorting this to what are they? It's called is it R16 and R17 or something? By shorting R16. And the way you do that is, I'll try and look at the video so that I see if I'm showing it correctly. Hi, Akshat. How are you? I can do that. Just a moment. Let me finish explaining what I was doing, and then I will explain it to you now. Welcome, Akshat. So we need to short that little how do you call it? That little resistor, so that we can make sure we get the clock directly. And what I've done is, usually it comes as a shape, but what I've done, it's going to be really hard to see, but there's a new solder near pin 20 that does that. I've soldered it in. So I've soldered a short. It's just they leave you a blank, and then, yeah, you wouldn't be able to see. I'm looking at the screen right now. You wouldn't be able to see. That's fine. Okay. That's okay. An intermission for a question. Hi, Akshat. Akshat asks, hey, can you exactly make me understand what kind of IoT application is an FPGA used for? So FPGAs are going to be used for applications where you have some specialized constraints, where it's going to be difficult to use a microcontroller. Say something like you need to make a spectrum analyzer or a spectrum observer for radio frequencies. That requires you to run DSP algorithms at something like on the gigahertz scale, and it's quite difficult to find microcontrollers that are going to be running at those speeds. That's number one. And then another thing is, you might need a lot of pins, and moving those pins, moving the data from a lot of pins through your microcontroller could be hard, and then you end up there. Or you have some sort of like specialized driver, or you want to drive something special, and the way you drive it is going to be quite difficult to achieve with a microcontroller. These situations are very common. One of the ways we use it at work is we make a MIPI to USB bridge. We make a MIPI to USB bridge that can do something like 3 gigabits per second of video data through that bridge without having a microcontroller. That would be very difficult to do from a microcontroller. Number one, because MIPI is a very complicated standard. Number two, you need a lot of pins. Number three, it assumes that you have a lot of primitives that you can work with, but that you don't really have on the microcontroller. So they're a little different. You use them for different things, and some of the times they are they're used in tandem with a microcontroller, and sometimes from what I've seen, you can even implement a microcontroller. Well, you can implement a system on chip on your FPGA and use that. That's kind of what you use an FPGA for. Does that answer you, Akshat? I wonder. By the way, we have a community. We have a community down in the description. It's a Discord link. Join us and you can discuss this in detail and with diagrams and links and all of that stuff. And I don't have to. I can answer those questions there much better in time. So, anyways, as I've said, we've connected that oscillator. So what I think we want to do is I want to go back and use this as a model. So the code I wrote here to change the code that we have so that it works better. Hey Bartholomew, thank you for showing up. Let's do this. So the next thing we're gonna do now is we need a clock signal. The first silicon blue primitive we want to get rid of so that testing becomes easier is the silicon blue high frequency oscillator. So, and what we use that for is it gives us a clock signal, and we want to get rid of that. And from the documents, it says, what document was I looking at right now? How to use the oscillator. So we need to short it. I've shorted it, and then it says that I think it says it's IOB25BG3. So let's go look at the schematic for this thing and see if we can find it. Here's the oscillator. Cool. So the oscillator goes into so oscillator I see out clock 12M FT, which is where? IOB, let's see. This is going to 8. That's not what I want. Oh yeah, here you go. IOB 25BG3. So okay, cool. Let's go find that pin on the thing. IOB pin 20. Do you see here? IOB 25BG3. That's where the clock in thing is going to. So let's make a clock. For all those who are joining, there is a Discord link in the description. Join us on Discord and ask more questions if you need discuss. So let's ask more questions on the link on the comments. Let's actually go and actually make an input for pin 20. So the first thing we need to do is here we need to say I can do this. I can label this LED. I don't know if I want to label this. How did I label this before? Pico Ice Explorations. You can't just do that. Yeah, you can't just do that. Let me see. PCF. What can you do? Hash. Hash is how you comment. Okay, cool. So output LED outputs. Okay, so those are connected to those lines, and then we can do clock input. Hey Nathan, I'm doing really well today. Thank you so much for asking. How are you doing? Clock input, and then we can say yes, set IO, CLK, but we want this to be on this line, and we said that was on pin 20. So, and then we can also check for sanity. We can see lead green 41, lead green 41, lead red 41, lead green 39, lead blue 40. Let's see if those match. So yeah, if you see here, 39 green, 40 blue, 40 blue, yeah, 41 red. So those are the pins. We're just assigning a pin. That's what we did here. We assigned a pin to the clock. So let's see if we can actually change the behavior of our code now with the clock. So let's add an input here, no? Inputs, and then I want to do input CLK. I'll just label it that. And then the other thing we can't do is, instead of using the internal oscillator here, the wire for the internal oscillator here, I'm going to just use clock over there. So I'm going to wait for the positive edge of the clock, CLK. I'm going to stop just now for questions. I just want to remove this and remove this and remove this, so we make sure it's actually working. We remove the clock. We don't need int OSC. Where is that? We don't need it. Okay, we don't need that wire anymore. So this is counter register for slowing clock. Cool, amazing. So let's build that and see. Up here, build. Cool. I just need to be connected to build. Wow, I didn't know FPGA tools are like that. Up here, build. Let's see. Any questions so far? Any questions? Any questions so far? No questions so far. Cool. Yeah, so that build actually. Let's run it with iceprog. iceprog build. Isn't it in build? Oh, it's in build. I think it's in default. I think it's in hardware. I think bin. It's coding it. It's developing it. Let's see. Oh wow, is it broken? Looks broken. It's not broken. It works. It works. Yeah, we get our blink back. I do notice it's so much slower, and it's slower likely because we're slowing it down by quite a lot. If you think about it, this is a 12 megahertz clock, and the one that we were using before was a 21 megahertz clock. So maybe we don't need to slow it down that much. Maybe we don't need to slow it down that much. So maybe let's go like 15, and then here let's use 15 rather. 15. I think so. Let's do that and see if we affect the speed. So look at that speed. Let's see if it goes faster. If it goes faster, number one, we know we are using our own clock. We've removed one silicon blue, and we know we are using our for now. Okay, and then I'll use iceprog build iceprog and program that. Hey Nathan, isn't that awesome? Look at that. That's so slow. That's so fast. That's amazing. Maybe it's a bit too fast. Maybe it's a bit too fast. Okay. Let's slow it down a bit. Let's slow it down a bit. Let's say let's do a 24-bit. 24-bit. Okay. No. Actually, let's do a 20-bit. And then let's actually just slow it all the way down to 19. That's actually cool. Let's do that. Yeah, that's cool. That's so cool. I think so as well, Nathan. That's quite cool. Yeah. Okay, I'm gonna run that one. That's not actually not too bad. That's actually not too bad because actually you get it. Yes. No, 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 not yet, not yet, Nathan. So right now we're no longer using the silicon blue primitives for the clock. The next thing we're gonna do now is actually go do it. Let's go remove the silicon blue primitives. This silicon blue primitives for the RGBA driver. So we've removed one part of the silicon blue. We've removed the silicon blue for the high frequency oscillator, and then now we want to remove the silicon blue for the RGB driver. Once we do that, then we can move to like writing tests for this thing. And I think if I remember correctly, the other week when I was doing this, in here all I had to do was just assign. Assign should make it work. Assign should be like, yeah, just make it work. Yeah, you see this? Yeah, that's it. We can do that. We can assign. We assigned them before. Okay, cool. I'll assign them after, because the reason I'll assign them after is just because so that the code kind of looks the same. Okay, so that the code looks the same. So assign this to the symbol, assign that to the symbol, assign that to the symbol. I see what I need to do. So lead red, lead blue, lead green. Okay, cool. So here, let's do to stop using the silicon blue primitives. Yesterday I had a really hard session. I'm answering Nathan. Nathan's asking, what made you change your mind? And I'm assuming it means what made me change my mind about using the silicon blue primitives. Yesterday I tried to write a test bench for the CPU that we built, which came from a recommendation when one of my co-workers reviewed my code at work, and they were like, yeah, this is good, but the more complicated your CPU gets, and when you want to test it, it's going to be very difficult to do debugging if you do not have a test bench. And a test bench in Verilog is sort of like, how do we say this? A test bench in Verilog is like unit tests and integration tests. So yesterday we tried to write unit tests and integration tests for this thing, and it just did not work, because it's impossible to stub out, to mock the silicon blue primitives. Well, it's not impossible, I just don't know how yet. And I want to keep on going with the CPU, not stop and learn how to mock silicon blue primitives. So the reason I'm doing this is so that I can actually write a good test bench for my code. Yes, it's hard to test something you don't know. Exactly. Amazing. You actually answered it. So assign lead blue. We can just do lead blue equals to R, and then we need to read ROM, and then PC, and then in PC we need to get the 3 and the 0, the 3 last bits, and then here this one is affected by 2. I think this ends here, and then this is affected by 2. I think that ends like that. Yeah, I need that. Assign lead RGB green because yeah, I want to do this. So R PC 3 0 and that, and then that, and then 2, and then 1. No, not 2. No. Yeah, 1, because it's 3. It's 3 bits. Assign lead red is equal to stop R ROM PC 3 0. And then this one, let's use the 0th bit, or the least significant bit. So let me, and then here, actually what we want to do is delete this. we want to delete this whole block down here because we don't need it. RGB, SV. That's kind of it. So if in Nathan's words, we own all the code here. Yeah, cool. We own all the code here. So let's see if this runs. I highly doubt it's that easy. Is it really that easy? I don't think so. I think it's gonna crash. I don't think it's that easy to like just strip it out, up your build. It's gonna crash for sure. What? Okay, cool. Hey, what? Okay, cool. So let's flash it. I'm calling a no-show. Let's flash it. It has to flash and then it has to do a reset. It worked! Oh, I noticed something. I don't know. Nathan, you might not notice. Do you notice how bright? It's much brighter now. It is much brighter now. And coincidentally, I think I know why. Yeah, it's blinding me. It's blinding me. It's much brighter now, and the reason for that is let's do a git diff here so we see. The reason for that is formerly I had this block of code here, and this block of code, if you remember when I was writing the first one, allows us to set the current to the lowest 111, the lowest level. And I think now, because we're not using a PWM, we're just pushing straight power into it, it's much brighter. It's basically binary bright. It's binary on or off. It's like full power, 3.3 volts or off. And previously we could have scaled the power that was going to that. And I think the way the scaling was working, if we use PWMs, this was adjusting some sort of, this is 8 bits, yeah? 1, 2, 3, 4, 5, 6, yeah. So this is some sort of like, 1, 2, 3, 4, 5, 6, maybe some sort of hex thing. Yeah, I don't know. But we were able to set the current really low, or rather to the lowest on it was. And now it just goes to full on, and it is so much brighter. It's so bright I can't look at it. It really is. I'm gonna disconnect it. It's a bit. There's a disco on my desk. Wow, that's actually cool. We did something. We stripped away the silicon blue stuff, and as a recap, let's quickly go through the code and see what happens. So because there might be someone new here who hasn't noticed. So we're making a module that's a tiny CPU, and then in that module we'll accept an input that is a clock, and then we have a couple of outputs, or three outputs, three LEDs. There's an LED red, LED blue, and LED green. All of these are connected using the PCF on the other side. And then we declare a 21-bit frequency counter that we're going to use to slow down the 12 megahertz clock that is coming in. And then we have a couple of registers for our CPU. We have general purpose registers. We have a program counter. We have ROM memory as well. And then what we do next is we count on our CPU, but we make a connection. We make a connection to one of the 19th bit in our binary counter of the CPU, and that's the only time the 19th bit. Whenever the 19th bit is set to a rising, we use that as our CPU clock. So we're making a much slower clock so that we can actually observe the LEDs blinking. And that's why when I started and it was really fast, I had made like a 15-bit clock. It was going really fast. So that's kind of what we did. And then in here we're just running through CPU instructions, and according to each one of them we're doing something. we can do it. We're doing these instructions. What we're trying to do is we're trying to make something that respects the RISC-V architecture. In any case, that works. Let's commit that and attempt again to write some tests, because I think we do have the test bench here. ls. Yeah, so this is what we did. Yes, this is what we were doing yesterday. Look, cat main. Okay, I can just main. We tried to write this test bench yesterday. If I run this test bench, it just insanely explodes. I can do it with Appio sim main tbv. It just goes, yeah, it just errors out, and it errors out because it can't find the things it needs, and it just doesn't want it. It just doesn't want us to, do that. So the thing I'm gonna do, let's try and emulate this test that I got from Appio a few weeks ago. There's a very simple test bench here. If we use it as a reference, I think we can write our tests for this thing really quickly. We have another maybe 20-30 minutes. We can do this. Let me clear the stuff. Git status. RM, RF, tiny CPU, yeah, all of that. RM dash RF main TBV. Git status. Okay, git add main git diff dash staged. Yeah. So this is remove all. Okay. Git commit dash v, and then in here. What application am I using to run the test bench? I will show you just now. What is it called? GTK Wave? Let me quickly go out and run an actual working test bench so we can see. It's GTK Wave or something like that. CD LEDs RTL plus Appio sim main tb.v. What is it called? GTK Wave. GTK Wave. Yeah, that's what I'm gonna use to run the test bench. Does that answer your question, Prapul? Okay. Or are you asking how Appio gives me? I'm very new to FPGAs, so I might have answered the wrong question. Appio also lets me run the test bench, basically doing that. Oh wait, that was a simulator. Prapul has a different question. How am I running the tests? So let's actually try that. Let's see. Appio. So I was simulating, and you're asking about testing. So Appio test. Yeah, so it's the same thing. It did, but it never failed. So it looks like it was a success. Yeah, so it's using Appio both sides. Okay, so did we finish writing our commit? No, we did not finish writing our commit. What did we do here? Remove silicon blue primitives. Okay, so add input clock signal, remove SBA for HFOC, remove SB, HFOSC. Remove SB RGBA DRV. Use external oscillator. Okay, let's do that. Git status, git push. Dude, Nathan, I'm very slow at typing. I like git pull. I know what is happening. I did some changes. Why am I? Git status. I'm not. Git config pull dot rebase. I'm not scared of doing rebases. Rebases false. Rebase false. Rebase true. Git status. Okay. It should be able to rebase. Yeah, cool. Yeah, git push. Prapul, I'm not using Vivado because I don't know Xilinx, and I'm using Lattice. And also I have an old. I have a very old. All my code runs on like a ThinkPad T470. So I have a very old computer. I can't run like anything that needs like. I can't even run Lattice Radiant, because I can't run OpenGL on this thing or something of the sort. So yeah, it's simpler than you think. And I don't know how to use Vivado. I've never tried Vivado. What is Vivado? Let's check what Vivado is before we keep going, man. This is. By the way, all the new people, we in the description there's a link to a Discord, which is our community. You can join us and ask all these questions and such. Vivado FPGA. Nathan, do you know what Vivado is? Is Vivado a joke? Let's check it out. Prapul, is Vivado a joke? I'm a new FPGA professional told me to use modern IDs. My question is Vivado a joke? Is this really what people use? The editor feature sets resemble a clunky IDE from the 90s. It crashes on me several times a day. Spews nonsense. Who doesn't love the no error classic? When was this? A year ago. In my company, we rarely use the Vivado GUI. Most things are done using TCL. The GUIs were nice for viewing RTL schematics and tracing elements. I'm sorry, Prabhu. I haven't used Vivado. I might learn it, but if it's an IDE, I'm probably not gonna learn it because I can already write this stuff. Is a software suite for synthesis analysis of hardware description languages design superseding Xilinx. Okay. No, not a problem, Prabhu. Don't feel bad don't feel bad. I'm just having fun. I actually like that you asked me to check it out. That's no problem. But people are making fun of it, so we can make fun of it as well, I guess. Yeah. So it's a design suite, and I use Appio. Appio does the exact same thing. It's open source, but it might not cover the same surface area of the supported FPGAs. No problem with you being a student. Maybe actually join our community and we can learn together. That's cool. Cool. we're done with that. So let's go back to writing our tests. Thank you, Prapul, for the questions. Today now I know. So let's actually do this. Let's write this test and make a I'm not gonna use that n. So let's actually ls and vim let's do main tb.v. Yeah, and then in here we want to add a time scale. 1 ns 1 ps 1 ps, right? I had this problem yesterday. I need to quit and restart it, and then I should have Verilog highlighting. Yes. Why do you have a swap file? Oh, I see. Yes. Okay. Let me see now. It works. So let's actually go in here. And then let's say here, module. I want to learn how to write Verilog the right way. So test bench, tiny CPU. And then I think that's that. And then in here let's add a register for the clock and device under signals. Yeah. So reg, somehow in my head I assume Verilog reg clock. Okay. CLK is equal 0, and then we want wire LED blue, LED green, wire LED RGB, LED red, LED blue, RGB, LED green, LED blue. Okay, so those wires, and then after we have those wires, we want to do main. Is it a main or a tiny CPU? I will do a tiny CPU. And I don't know if I even need the tiny CPU. And then hash, and then and then here I'll do DUT, device under test. I don't even know if this syntax will work. This actually was hard yesterday, and it will still be hard today. I think this has a comma. Okay, cool. So this takes a CLK, and then this takes a LED red, and then this needs to be red, and then this needs to be a comma. And then let's make all the other ones. Dot LED green, LED green, LED green. Okay. LED green, LED blue, LED dot LED blue, LED blue, LED blue. Okay, and then I think that, and then I can finish that and do that. Yeah. Okay, cool. And then let's do a 12 megahertz clock. What are you using? 12 MHz clock for testing, like we have on the other side. So always hash 42 CLK equals not CLK. I see what they're doing here. They're oscillating something. Are you building custom? Yes, we are doing. We will end up building a custom CPU, Prapul. We will end up building our RISC 532 embedded RISC5 RV32E CPU. That's what we'll end up building. But it might take a while. Might take a few weeks. Maybe months even. I don't know. I don't know about that expected LED. I know what is happening here. This is something I'm going to use for asserting against. So that's okay. And then integer I. This is just learning how to write the syntax for Verilog. This is really what I'm gonna do. That's crazy. It's not that crazy. It's not that crazy. There's don't worry. It's not that crazy. There's the manuals. All the manuals are online, so you can just do it. There's manuals online on how to do this. If you just go read the manual, you can do it. It's RISC-32. RISC-V is open source for a reason, isn't it? Initial, begin, and then I like finishing my stuff so quickly. So I don't even know if this will work. I have no problem with this going to a part 3, to be honest. I am in no rush. End module. There's manuals online and we can do everything as long as there's a manual. That's fine. Dump vars test bench. Okay. So dump vars, and then this takes in our TB0, 0 TB tiny CPU, and that's that. Is it too hard? No. It's only hard if you try and do it all at once. If you there's something called compounding. If you try a little bit every day, or as often as you can, twice a day or thrice a day, you can move very quickly. It's not too hard. It's actually, I wouldn't actually say it's hard at all, because we already, the first day we attempted to write a CPU, we wrote a CPU. And the first day we attempted to go into the RISC-V architecture, we managed. We actually implemented something that was working along with the RISC-V architecture. It only becomes really hard if you try and do it all at once, or you try and do everything too quickly. If you do that, then everything will feel very hard and it won't click. So what you want to do is you want to leverage something called compounding. And what that means is accept that the thing you want to do takes a while. And then once you've accepted that the thing you want to do takes a while, build slowly. And then take your time. Repeat things until you understand them. I'm sure Nathan is here. I don't know if Bartholomew is here. All of these are people who watch me day and day over, try and struggle with stuff. Sometimes I go 3 days and nothing works. And I try as hard as I can every day. And sometimes I just try and nothing works. But that doesn't stop me, because I try for an hour, and if I can't get it to work, I stop. And then tomorrow I'll try again. And then. At some point, things start to work. And then once they start to work, you start to actually know what is working. And then at some point, you can see a problem coming before it gets here. And then, yeah. So it's not too hard. It's actually it's not hard at all. It's just tedious. There's a lot of things to do. There's a lot of little things to do. A lot of little check boxes to check. And if you just focus on them, forget everything else in the world, and you just check this little one checkbox at a time, you will be shocked at what you can do in 3 weeks. You'll be shocked at what you can do in 3 hours. You'll be very shocked. So it isn't too hard. It just takes a while. And then there's another thing I learned. There's a saying I had the other day, and the saying went like, do not try to do in days what was done in years and months. So be patient. That's That's the best thing I can say, Prabhu. I don't know. I don't know if that helps you, man. Okay, cool. Oh, look, it's telling us. Nathan, it's telling us how to test it. Check. So it says we should simulate. Ah, this is cool. Simulate rising edges of the clock, and then it tells us what to do. Let's do this. That's just a normal for loop. So in here, I want to do for int, isn't it? They don't do for I equals 0. I is less than 12. We can do 20. It's fine. I is equals I plus 1. And then in here we can do a begin. Ah, okay. Yeah. I have an answer for that. Prabhul. Prabhul, do you have an FPGA? Well, you don't even need one. You can get any software and do simulation with it. So you can't understand the whole thing before you do it. When I was younger, that is what I would have tried to do. You can't read everything. You can't know everything before you do it, Prabhul. So pick one part, any part. It doesn't really matter. Pick the simplest part. Pick the thing that you feel is the simplest part, and just learn that one, and then learn the next thing after that, the thing next to that, and the thing next to that, and the thing next to that. So my suggestion of a plan is to do something small every day. That's my suggestion of a plan, rather than try to. You can't understand the whole RISC architecture before you do it. I don't understand the RISC architecture. I don't. I only understand what sorts of instructions they have. I understand how to implement R-type, register type instructions, because I understand how they work, and I understand that register 0 is always 0. Whether you write to it or whether you fetch from it, it's always 0. But if you come back and check next week, I'll understand more than that. I only understand the rest of it stuff, because the generations before us came from a place where they had to know someone so that they could get the book. We live in an age of the internet. You can find anything online. You can go read it right now. So don't try and read the whole RISC architecture. Just read the part you're implementing, and then implement that, and forget that, and then read the next part, and then implement that, and then forget that, and then you keep going. That's really what is happening. Just do one part at a time. So here, simulate 20 clock cycles. I would be very happy if this just ran and just failed, to be honest. Let's do an end here. Cool. And then so we can go in here and we can write some code. Okay. At pause edge CLK. I know exactly what to do here. At pause edge CLK, this means every time the clock rises, this is what that means. And I only just show this. Every time the clock rises, it's a problem here. This is a problem. There's two things that are happening that are problems. Not exactly problems, but let me what is finish? What is finish? Finish? Is that a thing? And then that is inside end. Okay, cool. I kind of sort of understand what is happening here, and I think this is going to be the end of our stream today. We need to now figure out a way how to assert things. I understand it. I've learned how to write a test bench. What we're doing here is we are, because of this comment, it makes me understand everything. So, and because I've written tests before. we're simulating rising edges of the clock. So inside here, what we need to determine is sort of what ROM. We might need to give our computer, our test bench, some ROM it can use. And then based on that ROM, we should be able to, you can give it like three instructions that that you understand what they should do. You can give it an increment instruction, an out instruction, and another increment instruction. Okay, let's make three ROMs, three ROM instructions, and then we hand them over to the CPU, and then we simulate, say, a few cycles of the CPU. And on every cycle of the CPU, we need to check that it actually executed the instruction that we gave it. So there's two things. I don't know how to give instructions. I don't know how to mock ROM here. And I don't know how to, after I've mocked it, I don't know how to give it to the CPU. Which also means on the other end, our instructions need to start being deterministic. But let's see. First part, I want to see if, can I just run this? The stuff I've written right now, this. How does it explode if I run it right now? Up here, CD, where are we? Tiny CPU. RPO test. We can try with RPO test first. This should fail. Seven. I see. This is a problem. And which are one error, syntax error in variable list. Okay, I don't know why that's a problem. Here, one. Is it because you expect a space? An SPS? Anyone who understands Verilog, please tell me if I'm whatever mistake I'm making. 14 syntax error. 14,600 syntax error. Why is there a syntax error here? Because of the unnecessary comma. And this may be space here. And this is an unnecessary comma. I think that's why you don't like it. Okay, cool. There is an end here. That's fine. And then this hash into that. That's okay. That's fine. And then is it because you want this to be like that? Okay, let's do that. Let's do that. Let's do that for now. Let's try and get this one running. This one feels like it's gonna run. Our test bench ran. That we don't have tests yet, so nothing is failing. But our test bench ran. Up here. Sim main TBV. If this starts GTK wave, I'm in. Sorry about my cats. Well, it started GTK wave from code we wrote. This is insane, man. We can write a CPU right at home. We can write a CPU at home without going anywhere. Look, mom, no CPU. Git status. Git add. So actually now, this actually makes me git check out. Git check out. Git check out. -b We have a CPU at home, man. Git check out. No, we have test for CPU at home, but that's cool. Git check out the let's do PR PR add test bench, and let's do that. Git add main maybe git commit -m building and running test bench. Next time we add assertions to this thing. And then I'm gonna do a git push, and then I know this is gonna get git push dash set upstream origin, and then PR add test bench. Cool. Yeah, so we're gonna make we're gonna add a pull request, and we're gonna walk through in the next couple of days or something. We're gonna walk through adding. I'm gonna have to go study, and then we're gonna walk through adding assertions so that we check that our CPU is running the way it should. And what that also means is now our CPU, now we're gonna have to implement, or rather change our ROM so that it has all these instructions. And then once we change our ROM so that it has all of those instructions, we need to check that the CPU is doing the correct thing according to the instructions. Those are the assertions we're going to write. Anyways, guys and ladies and gentlemen, and also special notice to Akshat. Yes, Akshat. Thank you to Akshat. Thank you to Nathan. Thank you to Bartholomew. Thank you to Prapul. Thank you all for coming to the stream today and leaving your comments and asking questions. That was such an amazing sessions. This is TDD. Yes. Well, it's not development, it's design. So it is TDD, but it's not like test-driven development. It's test-driven design, because this is not called development. This is called design, because you're designing hardware. That's why like when we go to run it, it goes. I don't know if you've seen when we do Control R ice prog. The bin that we flash is called hardware. Like it's a and you know. So that's why there's all of those steps, like you hear of synthesizing and all of this, is because it's actually they're like talking about hardware and making the hardware thing. Anyways, once again, I shall try and do my conclusion. Thank you all so much for coming. Thank you to Prapul, thank you to Nathan, thank you to Bartholomew, thank you to Akshat, thank you to all the people who've left comments and asking questions and are interested in this. It's really awesome to hang out with you guys and ladies. And I really appreciate this. Please, if you have some time, leave a like, leave a comment, subscribe to the channel. It really encourages me to keep going. And I'll see you tomorrow when we work on adding assertions to this test bench. And if you come to the Zephyr stuff, we'll probably be doing more mangling of the data on that side. Other than that, it's been awesome. Thank you so much for coming, and cheers, everyone. Amazing one.